This lecture is on aromatic synthesis involving many steps. From our starting material, which is just benzene, to something with a lot more functionality. We're clued in that we're going to have to use aromatic substitution from the fact that you're just starting with benzene. And at this point here, we've substituted that aromatic hydrogen with a carbon group, but there's also an alcohol and a methyl ether on here. But in some way, throughout the synthesis, probably at the beginning, we'll have to substitute that hydrogen. Now, the nature of that substitution is not so intuitive. If we look at this product, this will jog your memory from chapters past. We can see that it's an alcohol on one carbon, and on an adjacent carbon, there's this ether group. We only know really one way to get to that specific functionality. And this can come, if you haven't already started the problem, or if you're stuck just looking at this mess, this can come from an epoxide. And I just wanted to include this mainly for review. But this mixture of enantiomers as a final target product could come from this epoxide. And it's an enantiomer. Now you should be able to figure out how to do this synthesis just looking at what's been added onto the molecule. We're going to have to attack the less substituted carbon of the epoxide. We're going to attack it with a nucleophile that's going to give that methoxy group, and that's just methoxide. And so when a strong nucleophile / strong base attacks an epoxide, it'll attack at the less substituted carbon, the easier path. And this occurs just in methanol solvent. Okay. Well, that kind of gets to the specific functionality of the product, but now maybe it would be a good time to pause it and really try to go from here to here, and it's going to take several steps. But try and work that out. I'll give another hint in just a minute. So if you got stuck, you're going to need to go through this aromatic intermediate. Notice where the bromine has been added there. So pause it and try and figure out either from benzene to this structure or from this structure here, or ideally both. As I pointed out, the bromine is at this special benzylic position. And so in order to add that bromine on there, this must have been through a benzylic bromination reaction. And these work very well, and they're highly selective. And so we do benzylic brominations typically with NBS or with bromine and heat or light. And this reaction is successful because there's a benzylic hydrogen there that is substituted in this radical mechanism for the bromination to occur. Well, if we look at this piece, this is just a 3-carbon alkyl chain that's been added on to the bromine, or to the benzene, and that can happen through Friedel-Crafts alkylation. For this particular case, that would be the most substituted site on the molecule that's formed a bond to the benzene, and so we don't have to worry about rearrangement. And so from 2-chloropropane with an aluminum chloride catalyst, we can have this reaction occur. We do have to worry about over-alkylation in this case, because once you alkylate once, the product is actually more reactive because this is an electron-donating substituent. The product is more reactive towards further substitution than the starting material was. We can get around over-alkylation by starting with an excess of benzene. And so if you have an excess of benzene, your singly substituted product will be favored. So that's how we can obtain our benzylic bromide intermediate and high yield. When we look from going here to this pathway, it'll include reactions from the past primarily. We really only know one way to make epoxides, and by far the most common, if not the only way to make them, is from an alkene. And it can occur in one step, like we learned most recently, or in a two-step sequence as well. And so if we have this alkene conjugated to the benzene ring, we can react this with MCPBA, which is the most common peroxy acid, or alternatively, you could just form the generic formula for a peroxy acid. And either of these conditions are essentially the same thing and will work to form the mixture of epoxides. Remember, this planar intermediate, the oxygen can come from the front of the board or from the back side to give you that mixture. Now, going from an alkyl bromide to an alkene is one of the original reactions we learned. It's an elimination. We can accomplish this with a strong base. These are both identical sets of hydrogens, and they're the only hydrogens that would be able to be removed anyway. But this could be accomplished with really any alkoxide. It's a bulky site, a tertiary site, so substitution would really not be possible, and the only thing that's possible is elimination. So this would certainly work in very high yield, and it gives us a nice stable conjugated alkene as a product as well. And so this synthesis here overviews a lot of reactions that we've learned recently and not so recently, but it's a good one to practice in the future, or make something similar up when you're practicing for your next exam or even the final. Now I want to try another one. This one is pushing into the next area after monosubstituted benzenes, looking at disubstituted benzenes, where we'll have to make use of directing effects. When you look at this synthesis, again, we're starting with benzene, so we're going to have to substitute the hydrogen to get started. But eventually we're going to have to substitute two hydrogens, and they're going to have to be the ones opposite each other. Now, if you look at both of these groups, you've got a T-butyl group, which is just an alkyl group, which is a mildly electron-donating group. And then you've got the amino group. The amino group is a strongly electron-donating group. They're both electron-donating, which means they're both going to be ortho-para directors. Since these groups are para to one another, that's a good thing, because both of these groups would prefer directing the other in the para and ortho positions. But then we have to think about, well, which group can we add on there first? There's a problem if you add on the aniline, or if you add on the amino group first. If you recall, if you think about potentially creating aniline from benzene in some sequence of reactions, potentially we could react this in a Friedel-Crafts reaction. This would be a highly activated benzene. The problem is aniline has lots of issues, but aniline does not work with Friedel-Crafts chemistry, mainly because aniline is basic and it can interact with this Lewis acid catalyst, and it basically shuts down the catalytic effect. And so this won't work with aniline. So that's one thing to point out. Aniline has trouble with a lot of these reactions. If aniline could undergo this reaction, the major product would be para, especially with a bulky substituent like the T-butyl group. Okay, well, if that doesn't work, maybe we can put the T-butyl group on first. And so from benzene, we could use these conditions of T-butyl chloride and aluminum trichloride. That's classic Friedel-Crafts chemistry. But recall, you can also use an alkene and an acid catalyst, because both methods generate the same carbocation, and that's actually what entices benzene to react. And so you could work out this mechanism if you wanted to. It's once the tertiary carbocation is formed, the mechanism is identical to the Friedel-Crafts one. You could also use an alcohol here and an acid catalyst that forms the same carbocation. And so one of these positions will get substituted. Just like before, even though we have a bulky substituent, they could be far enough away on opposite ends of the molecule that if we want to increase the yield of mono substitution relative to over substituted products, we should use an excess of benzene. Once we have T-butyl benzene at this stage, it'd be nice to have a reaction that could put an amino group directly on the benzene, but we don't have one. And so you have to think of a route that would work. And it turns out there's multiple routes that will work for this reaction. One that we've definitely been over so far. But so you should try and figure that out. And then we'll go through the mechanism of the first part of it. Because this is an ortho-para director, we can nitrate the molecule. We'll actually form a bond, a carbon-nitrogen bond. And the major product will be the para product, mainly due to the steric effect of that T-butyl group. And so, as an alkyl group, it's an ortho-para director, but the para will be favored just due to the congestion of fitting another group right next to that T-butyl group. So from here to there, what we really need to do is just reduce that nitro group, which is easily accomplished using hydrogen and a metal catalyst such as palladium or nickel or platinum. And so this sequence is a bit shorter, and all of these reactions are in the current material. What I want to go through now is the mechanism of this step. And we've done a lot of these, and it's a nitration reaction. But see if you can go through the mechanism by yourself. And when you get to the appropriate intermediate, see if you can rationalize through resonance structures why it's particularly stable. So we know that these conditions generate the nitronium ion. That's one thing you'll have to know. And so the nitronium ion looks like this. It's extremely reactive. It entices benzene to form a bond to it and for a brief time break its aromaticity. Well, if that nitro group has to go into the para position, we have to use a pi bond associated with that carbon atom. And so we've added our nitro group on there. And that'll put, if we've added the group on here, there's still a hydrogen right there. And that puts the positive charge on the adjacent carbon. When we look at this carbocation intermediate, we should rationalize its stability, which explains why the group was directed to that para position. And so we can do this with resonance structures. We can see that when the positive charge is in this position, through resonance it can be distributed onto the carbon with the electron donating group. And so even though it's a mild electron donating group, it still stabilizes this position relative to the other ones on the molecule. And so the fact that that carbon can have the positive charge, that's one of the best spots for it on the molecule, and so you definitely want substitution to occur to put the positive charge on that spot in at least one of the resonance structures. So even though we can't draw an additional resonance structure, the fact that it's right next to the electron donating group is important. And surely we can draw another resonance structure that shows the positive charge on yet another carbon. And so there will always be at least three resonance structures you can draw that show the stabilization of that carbocation intermediate. Now from here, from really any of these resonance structures, we go back in and draw in our hydrogen. In order to regenerate the aromaticity, we have to lose this hydrogen. That sp3 site has to become sp2, and we need those electrons from the carbon-hydrogen bond to come into the pi system. And so we can show that occurring by starting our arrow at that carbon-hydrogen bond, and those electrons coming down to satisfy that positive charge. And so this will be lost as H+ into solution. Really, it's probably water that removes it, or it could be any base in the solution. But that takes us to the product. So again, these are all just resonance structures. For the mechanism, it's not always necessary to draw all the resonance structures. It's helpful in explaining the directing effect of the substituent. But you could have completed the mechanism just from this structure here. And so it's a relatively short mechanism.